Good evening. Welcome to this session. I hope you can hear my voice. Okay. So I'll wait for one more minutes, then I'll start. So in this session, I'm going to solve previous semester's questions. I don't know whether that has been solved in previous tutorial or not. Okay. So we have total of around 15 or 14 questions. So these are just basic question. You have to find out the transfer function, and also by you have to find out whether for a given input and the system equation, the output is bounded or unbounded for a particular input. Okay, so you have to find. Basically, we are moving ahead in the course. So in the last course, we have found out what is the about the type of system. So in this course, we have defined what is the transfer function. Okay, and especially we are focused on stability. So single input, single output stability. So based on that, I'll be doing questions. So before doing questions, let me ask you whether in the previous tutorial have you done these questions like previous semester NPTEL questions? Okay, you can respond in the chat box. Okay, not done. So I'll be quickly doing those questions. Okay. So I think other TAs are discussing general questions. Okay. So before doing these questions for about 5 minutes, I'll just discuss what is being covered in the week two, right? Okay. Okay, one more question. So whatever the professor is writing, so is there notes available with you? One more question. Okay, so I'll just discuss what has been covered in the week two. So in the week two, sorry, earlier week one was all about the system, okay, and about ODE and ODE with constant coefficients, non-constant variable coefficients, and homogeneous, inhomogeneous uh, output forces. Okay, so in this we'll focus on transfer function. Okay, so for a given equation. Okay, so this is the given equation for the mass spring damper system. Okay, with if t. So this is so we'll be using this is ODE. Okay, with constant coefficients. So you see N, C, K. These are constant coefficient, and this is inhomogeneous equation because we have force Ft. Right. If suppose this is 0, Ft is 0, then we have homogeneous ODE. In all of our equation, we will be having Ft with constant coefficients. Okay. So we talked about what is transfer function here. So transfer function is given by output by input. Okay. So Laplace transform of y of t, which is y of s, and Laplace transform of y of t, u of t is us. Okay. So if you see this equation, let me highlight this. So this is the transfer function. Okay. With initial conditions equal to 0. Okay, so all initial condition being taken as 0. So so while we are solving the equation, so you see this is xs, this is fs. Okay, so if you solve this, you'll get two responses. Okay, so one is free response and the other one is forced response. Okay, so the free response is due to the initial condition. Okay, and the other one is due to f of t. Okay, so what we do while we are driving the transfer function, we maintain this initial condition, or we take this initial condition to be 0. Okay, so that we can have the input and output relationship. Okay, so this is the definition of the transfer function where all the condition are taken as 0. Okay, you write output as y of s. If you see this, y of s equal to ps into us. Okay, where ps is the Laplace transform of pt. So what is ps? Ps is plant transfer function, right? Okay, so we have a generalized equation. So you see the highlighted. So this is the generalized equation where the coefficients are constant. Okay, so for the causal system, okay, so we have defined the order, right? If n is greater than m, then we say this is strictly causal system. Okay, so in the lectures also, like they have done some questions, okay, based on that, how you can say whether they are causal or not. Okay, so that is already done by the professor. Okay, so you can see, so we have to remember this. Okay, so let me change this. Okay, n is greater than m, then we have strictly proper transfer function. Okay, so ps equal to ns by ds. So ns is the numerator and ds is the denominator. So if you equate ds equal to 0, you'll get the roots. Okay, roots of that will be called as poles of the transfer function. Okay, and mostly all the analysis after that has been done based on the poles. Okay, and what you want is, we want poles to be in the right half plane. Okay, so this portion we want. If we have poles in this portion, we'll say the system is stable. If we have poles in the right half plane or on the imaginary axis, okay, we'll see the cases where the poles are on imaginary axis. Okay, if the poles are on imaginary axis, we call that system as marginally stable, and if we have the repeated roots, then we call it's unstable. Okay, so that has been done based on various questions. Okay, ABC questions that's already discussed in the lectures. Okay, we'll see while we are doing questions. Okay, so if we are having uh, roots in the right hand side, roots on the imaginary axis, multiple roots, or we call it as repeated roots. Okay, repeated poles. Okay, then what how the system is behaving. Okay, whether the system is stable or not for a particular input, or it is completely or it's unbounded for every bounded input, that you'll see through questions. Okay, so we have done this. So again, it's very important definition. BIBO stable, the system is BIBO stable if output remains bounded in magnitude for all time given any bounded input. Okay, so once you're giving bounded input for a particular plant, it should give you bounded output, right? Then only you'll call that system to be BIBO stable, right? Okay, so we have done various questions. So some observations here. I hope you have watched the lecture and complete derivation for BIBO stability. Okay, so that is there. So up to now, they have covered. So they have not covered effects of zeros. Okay, okay. So let me ask you any doubt in this theory portion. Then I'll directly go to the questions. Okay, so they have explained where your pole should be, right? Your pole should be in right hand plane. Okay, it should not be in the right hand. Sorry, it should be in the left hand plane. It shouldn't be on the right hand plane. Okay, and what about on the imaginary axis? So it's condition. Okay, you should not have multiple roots, right? Or repeating roots. Otherwise, the system is what? Unstable. So that we'll see while doing the questions. Okay. Okay. So let's first start with a very simple question. Okay, the response of the system to an external input is called. So it's very basic. So we have seen in the first week also, and on the second week also, it's being repeated, right? So there are two responses. It is first is due to the initial conditions, and other is due to the external input. Okay, so that is called as forced response, right? Shall not spend time on that. You already know. Okay. Response of the system is due to initial condition, and other is due to external input. Okay, so the response due to external input is called forced response, that you know. Okay, okay, you see this question. A second order system is governed by this equation its transfer function is. So all these questions are the assignment question that were given for the last or previous batch of this particular course, control system. So that's why I'm covering these questions. Okay. I don't know whether that's simple or not, but these are very simple questions. You just have to find the transfer function. Okay. So let me find out. Okay. So this is the equation and we have to find the transfer function. So you know what is transfer function? Okay. So y of s by u of s equal to ps. So this is the transfer function, right? So we have to find this. We have to find output. We have to find the ratio of output to input, right? Okay. So this is the equation. So let's take the Laplace transform. Okay. So just write the equation because space will not be there. Minus 2y. So these are function of t. I'm just writing y. Okay. Equal to u. Okay. Let me take the Laplace transform. So while taking the transfer function, I'll just write all the initial conditions are 0. Okay. So then we can find the transfer function. Okay. So initial conditions are 0. So let me write the full Laplace transform. So this is y square y of s. Okay. Minus s y of 0 minus y. This is single derivation. Okay. Minus 2 s y of s. So once again we take this s y of s minus y of 0 equal to UFS, right? So you know all the initial conditions are equal to 0. So that's why what I do. So this is initial conditions, right? So these are all equal to 0. Okay. So what will be the final equation now? S square ys minus 2s ys equal to US. Okay. So let me bring ys outside. So s square minus 2s equal to US. So it's very simple question. And what is the transfer function? Transfer function is y of s by u of s, okay, which is equal to 1 by s square minus 2s. So this was very straightforward and simple question, right? 1 by s square minus 2s. So let's see the options, right? So this option is correct, right? So very simple. We're just starting, okay? A second order system is governed by this equation. Its transfer function is, so to get the transfer function, take the Laplace transform, okay? So you know, to obtain the transfer function, you have to take the initial conditions to be 0, right? So I've taken the Laplace transform, you see. So this is the Laplace transform with all the conditions, and then I'm making all the initial condition to be equal to 0, right? Y of 0 and this y dot 0 is also equal to 0. Okay. So any doubt in this particular question? It is very simple question. Take the Laplace transform and get the answer. Simple. Okay. So you're not concerned whether the pole is in right hand or left hand side, right? Any doubt in this question? Okay. It's a very simple question. This you have to answer. The transfer function of a causal system plant is. You can type the answer also in the chat box. Very simple. So this is already discussed in the class. Okay. The transfer function of causal system. Okay, let me go back and see where it is discussed. Okay. So these are the notes. Okay. You see here. So this is the equation, the generic equation that was there, and we found the transfer function. Okay. So we're just finding out the relationship between the orders of numerator and the denominator. Okay. So you see here, just focus on this part. Okay. So just focus on this part. Okay. If n is greater than m, that is strictly causal. Okay. What is n? You see here. the order, right? Order of the equation. Okay, that's clearly mentioned in the here also. You see, if n is greater than m, then it is strictly proper transfer function. Okay, so you have ps equal to numerator n is ts. Okay, so the order of numerator is what? M, and order of denominator is n. And if n is greater than m, that's strictly proper transfer function. Okay, and that is strictly causal here if you see. Okay, so the question was about that. Okay, the transfer function of a causal system plant is proper. Okay, so I'll just again go back and you see this. Let me highlight in the other color. You see this point. Okay, n is greater than m, we call it strictly causal. Okay, and if you see here, okay, strictly proper transfer function. Okay, so the transfer function of a causal system is proper. Okay, any doubt in this? So that's already discussed. Okay, okay, so now we'll be doing all the numericals. Okay, the poles of the transfer function of the system whose governing equation is. Okay, so first what we have to do, so this is the governing equation. You have to take the Laplace transform, consider all the initial condition to be equal to 0. Okay, then what we have to do to find the poles? So let me write, y of s by us p of s equal to ps, right? So I will just write what is y of s. This is the output, this is input. Okay, ps is plant transfer function. Okay, okay, this is there. And once we find ps, once we find the transfer function, so it will be equal to ns by ds, where ns is numerator and ds will be denominator. And to find the poles, what we'll do, we'll put d of s equal to 0, right? Simple. Okay, so I'm just discussing what we'll do. First, we'll find the transfer function, and second, we'll put the denominator of that transfer function equal to 0, and we'll find the roots. And those roots will be the pole of that transfer function. Okay, so let us do it. Okay, so let me write the equation first. Okay, please check if I make any mistake. Please feel free, okay, to correct that. So this is the governing equation, and you have to find the transfer function. Okay, so directly I'll make all the initial condition to be 0. I'll take the Laplace transform, right? Okay. One more time I have to check. Okay, everything is correct. Plus 2. Okay. Okay. Let me take the Laplace transform. S square y of s. Okay. Minus 3s y of s minus 4 y of s. Okay. S square u of s. Okay. Plus 2 s u of s plus 2 u of s. Okay. So let's bring y of s. So let's take that common. So the equation is s square minus 3s minus 4. Please watch for coefficients. Okay. So let me take y of s common. S square plus 2s plus 2. Okay. I think I'm correct. Okay. So y of s by u of s is equal to s square plus 2s plus 2. Okay. Square minus 3s plus minus 4 equal to 0. So That's what I was discussing. So numerator by denominator, right? So here ns is s square plus 2s plus 2, okay? And ds is equal to s square minus 3s minus 4, okay? So this is your transfer function, right? So this is the transfer function, okay? And we have to find the poles, right? The poles of the transfer function who's governing. So how to find the poles? We have to put ds equal to 0, okay? So s square minus 3s minus 4 should be made equal to 0, okay? So the root of this equation will be the pole of the transfer function, right? Okay. Okay, so let me find the roots here. Just see whether I'm making mistake or not. Okay. So according to this, the roots are what? S equal to minus 1 and s equal to 4. Okay. Just check. Minus 1 and 4. So these are also the poles, right? So right here, poles of transfer function. Minus 1 and 4. Okay. If you plot in S-plane, okay, so you'll plot in minus 1 here and plus 4 here. Okay, so you see, so this is coming in right half planes. Okay, so we call this as the system would be unstable. Okay, so that is not asked. We are here just to find out where the poles are. Okay, minus 1 and 4. Just check whether I'm doing any mistake or not. Okay, minus 1 and 4. Okay, very simple. So the equation was given to me. I took the Laplace transform, found out the transfer function, and made the denominator to be equal to 0. Okay, and once I got the roots, and those roots are the poles of the transfer function. So in this given question, the roots are minus 1 and 4. Okay, so minus 1 and 4. Okay, I hope this is correct answer. Okay, any question? Okay, you can ask any question in case you have any doubt here. Okay, so it was also a very simple question. Okay, okay. So the zeros of transfer function of the system whose governing equation is. So in the previous question, we were asked to find the poles. In this question, you have to find the zeros of the transfer function. Okay, I think the two questions are same. Okay, I hope they are same. Okay, so the transfer function y of s. Let me again write it the transfer function. So y of s. Oh, let me write as transfer function. Just p of s equal to. Okay, copy this. Okay. So this was the original transfer function that we have derived. To find out the zeros, what we do, we put numerator to be equal to 0, right? S square plus 2s plus 2 equal to 0. So then we will find the roots, and those roots will be the zeros of this transfer function, right? So that's what we do. So let us find the roots. Okay. So you see, so let me to find the root. So I'll use this formula to find the roots. 2 into a, right? So for the general equation should be this: as square plus bs plus c equal to 0. Okay, so this equation is in this form. So the roots will be s equal to minus b square, okay, minus 4 1, this is 2 into 2 into 1. Okay, so I'm just using the general formula that you all know. So this is 2 square is 4, 4 minus 8, so this is minus 4. Okay, so minus 4 I can write as 2j, okay, by 2. So this is minus 1 plus minus j. So two roots are minus 1 plus j and minus 1 minus j. Okay, and the roots of this equation is also zeros, okay, of the transfer function. Okay, so this is the correct. So this was also very simple. So in the 4 and 5, so we are given equation, we have found the transfer function and we are finding the poles and zeros. Okay, to find the poles, you put denominator equal to 0 and find the root, and those roots are the poles of the transfer function. Similarly, to find the zeros, what you do? You equate the numerator function to 0 and find the roots, and those roots are the zeros of the transfer function. Okay, that's what we have done. Okay, so any doubt in this question? Question number 5. Okay, so these questions are on basics of transfer function, just finding poles and zeros. Okay, so next question we'll do. Okay, question 6 to 8. Okay, calculate the expression for unit step response of system whose governing equation is given. Okay, so we have to find the step response for this. So u of t is okay, this is unit step function, right? Okay, let's calculate the expression. Okay, so the equation is this. So can you do this question? Very simple. Can you find the transfer function, or at least find y of s in terms of p of s and u of s? Okay. After that, we will proceed. Can you find y of s? So what you have to do is simply take Laplace transform. Okay. Just take Laplace transform. Very simple. I will not ask you. I'll just give you 30 seconds to drive the Laplace transform. Okay. Then I will do. Okay. Just take all the initial condition to be 0. Okay, I hope you have found the Laplace transform. So let me do it. So taking Laplace transform, s square, okay, s square y of s plus 6s y of s plus 5 y of s equal to u of s. I hope you're getting the same. Okay, let me take y of s common. S square plus 6s plus 5, okay, equal to u of s. Okay, so y of s is equal to u of s. So s square plus 6s plus 5. Okay, so let me factorize the denominator here. Okay.
S plus 1, S plus 5.
Yeah, same. I'm just here. It was 5, correct? So y of s plus 1 is plus 5, correct? So this you got, right? Very simple. So what you have to find out the steady state value of the output as time tends to infinity. Okay. So we have learned. So tell me. So we have to find out this when t tends to infinity. Okay. We have to find out what is the y of t, right? So how to find out? We have learned some theorems, right? In the first week. Can you tell me which theorem should I apply here? Okay, the steady state value of the output. Okay, as time tends to infinity. So you have to find out limit t tends to infinity y of t, right? So do you know which theorem? Like two theorems you have studied, right? Initial value theorem and final value theorem. So which theorem should I apply here? Can you tell me?
Sir, 1 by 5.
1 by 5. Okay, you're telling me answer. Which theorem should I apply? So how did you do that to reach the answer?
Sir, when will be value put at t tends to infinity, so
Mm-hmm.
e to the power minus t will be 0, then only value will be find 1 by 5 is the
Mm-hmm.
0.2,
Okay, okay, I got.
0.25.
Mhm. So you're saying first what you have done, this U of S, you have put 1 by S, right? S plus 1, S plus 5. Okay, then let me just bring this and you have written as A by S plus B by S plus 1. Okay, plus C by S plus 5. So this you have done, and then you correspondingly you have put this limit. Okay, that is also fine. So I was asking you, so you have studied about theorems, right? Initial value theorem and final value theorem, right? So this we can apply like s tends to 0, s into y of s, right? This also we can do. Like we don't have to find the y of t. Okay, in the Laplace domain we can find out. Okay, let me write using final value theorem. Okay, that is also correct, using final value theorem. Okay, so do you remember this? So let me shade this. Do you remember this from the first week? Okay, so same thing we are finding out. Okay, so let me find out limit s tends to 0. Okay, what is y of s? So y of s is us by s. Okay, this one. So this is y of s. Okay, so I'll put this 1 by s into s plus 1 into s plus 5. Okay, so this cancels out. So limit s tends to 0. So this is s plus 1 and s plus 5. So if you put the limit here, so if you put s equal to 0, you'll get 1 by 1 into 5, right? So which is equal to 1 by 5. So you got the correct answer, which was 1 by 5 is what? 0.2. Okay. So yeah, we now take that. So what you did first, no need to find y of t. Okay. In the Laplace domain itself, using final value theorem, you can get the steady state value. Okay. So which is equal to zero point 0.2. Okay. So other way is what? This is y of s. Okay. Solve for ABC, you will get y of t. Okay, then you can use this limit t tends to infinity and you will get the same answer. Okay, that we will do. Okay, in the next question. Okay, so see, option 3 is correct, like 0.2. Any doubt in this? Okay, any doubt? Simple. The governing equation was with us. Okay, it is with us, and we just took that Laplace transform. Okay, and what it was asked is the steady state value. Okay, so I had applied final value theorem, which is limit s tends to 0 s into y of s. Okay, so directly if I put s equal to 0, I will get 1 by 5, which is equal to 0.2. Okay, okay, let me do the other part of this. Okay, the coefficient of e raised per minus t term in the output function. Okay, so to find out the coefficients, I have to solve this.
minus 0.25.
Okay, let's find out first. Okay, so this is the equation. So let's solve this. Okay, so this is given, which is equal to 1 by s into s plus 1 s plus 5. Okay, so what we do to find out the coefficient of a, okay, multiply both the side by s and put s equal to 0. Simple. So let me do the first step. Okay, so multiply both the side by s. If you multiply both the side by s, okay, it's very simple, you can directly do it, but I'm doing it for the first time, so let me do this. Okay, so it will be a plus bs s plus 1 plus cs s plus 5. Okay, so let's put s equal to 0. So if you put s equal to 0, okay, on the left hand side you'll get 1 into 5, 1 by 1 into 5, and you see these two terms will be equal to 0. Okay, so you'll get a as 1 by 5. Okay, so similarly the same process you'll follow for the b and c. Okay, so to find b, what I'll do, I'll multiply equation. Let me write equation. This is equation 1, so I will multiply equation 1 with s plus 1. Okay, then I will put s equal to minus 1. Okay, so let me directly do that. Okay, so b will be equal to, if I put multiply with s plus 1, so, and if I put minus 1, so it will be equal to minus 1. Okay, minus 1 plus 5, so which is equal to minus 1 into, so minus 1 plus 5 is 4. Okay, minus 1 by 4. Okay, similarly for c, what I will do, I will multiply both the side with s plus 5. Okay, then I will put s equal to minus 5. Okay, directly I am writing here, so which is minus 5, so minus 5 plus 1. Okay, which will be equal to minus 5 into minus 4, which is plus 1 by 20. Okay, so now I have values for a, b, c. Okay, so I'll highlight those values here. Okay, so I've highlighted those values and I am putting it. So y of s, so a is given as 1 by 5. Okay, s, okay, so this is 1 by 5 s plus minus 1 by 4 s plus 1. Okay, plus 1 by 20 into s plus 5. Okay, so then find the inverse Laplace transform. Okay, so what is the inverse Laplace transform? This is 1 by 5. Okay, minus 1 by 4 e raised per minus t. Okay, plus 1 by 20 e raised per minus 5t. Okay, I hope up to now it's very clear. Okay, so this is the system response. Okay, in the question what they're asking, the coefficient of e raised per minus t. So which is equal to, so what is that coefficient? So this is the coefficient, which is minus 1 by 4. And my 1 by 4 is what? 0.25. Okay, minus 0.25. Okay, so this is correct. Second. I hope you're getting the same answer. Okay, so let me repeat what I had done. So in this, we have to find the coefficient of e raised to power minus t. Okay, to find the coefficient, what we have to do? We have to solve this. Okay, once we get the solution in Laplace transform, we have to convert it back into you have to get the inverse Laplace transform. Okay, so we got ABC. Okay, so this was the solution we got in Laplace domain. Then simply we have to find the inverse Laplace transform. It was very simple. Okay, so any doubt in this question? Okay, I hope there is no doubt in this very simple question. Okay, so again, this eighth question is follow question. Okay, the coefficient of e raised to power minus 5t term in the output function is. So what is the coefficient?
0.05.
Okay, 0.05.
0.05.
Okay, which is 1 by 20, right? Which is 0.05. You calculate that. Okay, so it's very simple. The coefficient of e raised to power minus 5t. Okay, I hope there is no question in 8th, 7th, and 6th. Okay, very simple. And you know, we have calculated y of t, and in the first question itself, if you calculate y of t and directly what it was asking the steady state value. Okay, so you can do this also. Limit t tends to infinity y of t. Okay, so which is equal to, if you put t tends to infinity in this, okay, plus 1 by 20 e raised to power minus 5t. Okay, just put t tend to infinity, so you know this will be equal to 0 and this will be equal to 0, and the final answer will be equal to 1 by 5, right? This is also one of the way to solve this question. Okay, but we used final value theorem. Okay, because we from Laplace domain itself, it was easy to calculate that. Okay, so you can do it in this way also to get the sixth question's answer. Okay, so this is how we did it. Use the final value theorem, but you could have found out the y of t and put limit t tends to infinity. You get the same answer. Okay, any doubt on this? 6, 7, 8? Any doubt? Okay, then we'll do the next question. Okay, 9, 10. So calculate the unit step response of the system whose governing equation is. Okay. Okay, again same questions, and this question I think you do it. Okay, same question, similar to 6 to 8. Okay, so the governing equation is this. U of t. Okay, and ut is unit step response. Okay, unit step. Okay, input is unit step, and you have to find out the unit step response. So please find the Laplace transform of this. So I'll be doing, just parallelly do with me. A square y of s plus 5s y of s equal to u of s, right? I hope you're getting the same. Y of s is s square plus 5s. Okay, let's take this common. So it is s plus 5. Okay, so are you getting the same? Can you tell me what are the poles for this transfer function? Can you tell me the poles? Just seeing this equation. Correct. 0 and -5. Good. Okay, so let us do our question. So the steady state value of the output. Okay, let us find out first y of t, right? So, u of s is equal to 1 by s. Okay, so I'll write it here, which will be equal to 1 by s. So it will be equal to 1 by s square s plus 5. Okay, s square s plus 5. Okay, so how to find this? A by s plus b by s square plus c by s plus 5. Okay, this is how you find it. Can you find the coefficient here? Simple ways, I think final value theorem maybe I can apply here. So what does final value theorem says? If its t tends to infinity, y of t should be equal to limit s tends to 0 s into y of s. Okay, limit s tends to 0 s into y of s is equal to 1 by s into s plus 5. Okay, limit s tends to 0 1 by s into s plus 5. Okay, so according to this, if you put s equal to 0, you'll get, right, it is infinite. Okay, so this is one way. Other way is finding this y of s. Okay, so also one observation here. So, but just by looking at this y of s square, okay, so you'll know key y of t. If I just write, let it be some coefficients, right? So I'm writing in red. Okay, so a by s, some constant coefficient will come. Okay, so you will write some coefficient. Let it be a only. Okay, so a square, some e t raised for e minus some term will come, right? T term will come, and it will come some c a raised for minus 5. This will come, right? So if you see this term, you can just focus this on this term. Okay, if I put this, limit t tends to infinity. Okay, so what will happen? So this term will become 0, because at infinity e raised for minus 5t will be 0. But if you see this t term, okay, this will go to infinity. Okay, no need to solve for ABC, but just by observation also you can do. Okay, because s square, right? S square, you have seen the Laplace transform. Okay, we'll just go to the notes. Okay, so here you see here. So I want you to focus on this. Okay, if I take the inverse Laplace transform of 1 by s square, what I will get? So let's suppose we found the coefficient b. Okay, let's assume we got the coefficient b. Okay, but we know the inverse Laplace transform of 1 by s square is what? T. Okay, let me not write this. Okay, so you'll get something a plus bt plus c e raised per minus 5t. But if you put this limit t tends to infinity, if you put this, a plus bt plus c e raised power minus 5t, you know, this term, the second term, okay, because of this second term, you'll get answer as infinite. I hope you're correct. Okay, any other answer? Any other, since you have solved, any other solution to this problem? Okay, by final, I have applied the final value theorem. I got the infinite answer. But if you solve y of s and find the coefficient ABC and find the inverse Laplace transform, what you'll get? Okay, you'll get a plus bt plus c e raised power minus 5t. Okay, because of the second term, t term. Okay, because it's growing, right? As t is going to infinity, the second term is also growing bigger. So that's why the whole term y of t becomes infinite. Okay, because of that. So its answer is this last. The steady state value of output as time tends to infinity is infinity. So any doubt in this question? Any doubt? Or you want me to explain once more? I hope I'm making it clear. Okay. So, okay, let's do the second part of this. The coefficient of e raised per minus 5t term in the output function. So now you have to find out the coefficient of c. Okay, let's only find the coefficient of c. Okay, I'll just copy this. Okay, any answer? I'll solve, but any answer you want to give, which is equal to what? 1 by s square plus 5. Okay, so what to do to find the coefficient of c? Let me call this equation 2. Okay, so what I'll do, I'll multiply both the side by s plus 5. Okay, so this is s square. If I multiply, because s plus 5 numerator and denominator gets cancelled, a s plus 5 by s, okay, plus b plus 5 by, okay, so this is s square plus c. Okay, and what I can do, similar process, I can put s equal to minus 5. Okay, so minus 5 square, so this a and b term gets cancelled. Okay, so you will have only c, so c is equal to 1 by 25. Okay, so what is 1 by 25? So I'm getting 0.04. So c is equal to 0.04. Any doubt in this question? Any doubt? Okay, so the question number 10 is very simple, but you see the question number 9. Okay, question 10, answer is 0.04. Okay, okay, I'm just waiting for your doubts. In case you have any doubt, you can ask here. Okay, otherwise, we'll go to the question number 11. Okay, consider a system whose governing equation is given, the input for which the output would be unbounded. Okay, you have to find out the input for which the output for this equation will be unbounded. Okay, let's first write the equation. qt. Okay, so let's find the Laplace again. Simple. Y of s is equal to u of s by s square plus 4. Okay, so this is the, so if I bring u of s here, okay, so this is Planck transfer function, right? So its roots are what? Plus minus 2j, correct? So I'll plot the roots, okay, here. This is imaginary axis, this is real axis. This is S plane, okay. So I will highlight with red color. This is 2j and this is minus 2j, okay. So these are the poles, okay. And we have to find out the input for which the system output would be unbounded, okay. So just looking at this system, what you can say about the system, since roots are lying on the imaginary axis, so this is marginally stable, right? So you studied in the lectures also, okay, though with the strict definition it's an unstable system, but since roots are lying on the imaginary axis, so these are non-repeating roots. So let me write it here, non-repeating roots, okay. If roots are repeating, then straight away we'll say this system is unstable, because if you find the y of t, you will get the unbounded, you'll get the t term, and for whatever input you give, your output will be always unbounded, that we'll see, okay. So these are non-repeating roots. According to the definitions, it's a marginally stable system, okay. So let's check for input, right? So y of s is equal to u of s by s plus 4, okay, square plus 4, okay. Okay, so what is y of s? Y of s, if I put u of s equal to, if I put the first option, first is 1, right? So Laplace transform of 1 is what? 1 by s, right? So you will get this, okay. So what you can tell about system? Okay, let me first go once again and refresh what was covered in the lecture, right? Then you'll get more clarity. Okay. So okay. So we have covered question. So you see in the first question here, in the week, so the roots are lying in the left half plane. Okay. So what was the observation? Okay, we are getting as t was tending to infinity. So I'll just highlight with the color. Okay, you see this. Okay. So you're getting the bounded inputs. Okay. And you see here s plus 1. Okay, similar term we got s plus 1 here, right? So here, so we are calling this as what? Marginally stable system. Okay. And in other question, if you see this question number 3, okay, so this was the equation, right? Okay, s square s plus 1. I think similar equation now we are getting is s square plus 2. Okay, so you're getting this type of response. If you see this, you for a unit step response, you're getting this. Okay, for this particular question, minus 1 t plus e raised for minus t. Okay, because we are having repeated poles at s equal to 0, right? Because of that, we are getting the response this. If you focus on this term, For repeated poles on imaginary axis, you will get t term. Okay. Similarly, if you see here for this fourth question, okay. So for the fourth question, okay, fourth question, one root was lying. So if you see here, one root was lying on the right hand plane. That's why if you see the y of t, which is shaded, okay, you're getting this term, e raised to minus t. Because of that, you'll get your output to be unbounded, right? So based on those discussions, so we have defined this, right? You see this lecture, particular lecture, okay? So for a particular question, s into s plus 1, okay? So what can we get? So let us find the poles here, okay? 0 and plus minus 2j, okay? So these are non-repeating poles, right? So again, I have written, I think, yeah, these are non-repeating rules. But if you see the second option is u of t equal to sine 2t. Okay, I'm just checking this option. Okay, let us put u of t as this. So if you find u of s, which will be equal to 2 by s square plus 2 square, okay, which will be equal to 4. Okay, let's put in this y of s equal to p of s into u of s. Okay, so p of s is s square plus 4 into 2 into s square plus 4. Okay, so now what you can see, s square plus 4 square. Okay, so if you try to find y of t, okay, you will get the t term, this e of t term, or t into e of e term, because of this. Okay, I'll say repeating, it is not a transfer function. Okay, but okay, let me try to solve this. Okay, so it will be lengthy process, so let me try to solve this and we'll find out y of t. Okay, then we'll see whether s square plus 4 whole square, what we are getting. Okay, we are getting t term or e of t term, where if we put t tends to infinity, it will be bounded or not. Let's check it. Okay, okay, so what we know, so we know Laplace transform of sine 2t is equal to 2 by s square plus 4. Okay, so let me use two identities here. Okay, t into f of t Laplace transform, okay, is equal to minus dfs by ds. This is one, and again I will be using is this 0 to t tau f of tau d tau, okay, which is equal to fs by s. Okay, these two identities were discussed in the first week. So let me show you where it is discussed in the lectures. Okay, so if you go to the first week's lectures, okay, let me, okay, so here, okay, so I'll just highlight those things, those properties here. Okay, complex differentiation theorem, and this one is real integration theorem. Okay, that's what we'll be using it to get the inverse Laplace transform. Okay, t into ft is minus dfs by ds, and if you want to divide f of s by s, you have to integrate on the other side. Okay, let me do it and show you. I'll be using these two properties, okay, differentiation and integral. So we'll be starting from Laplace transform here. Okay, so let's find the Laplace transform. Okay, so what I'll do, I'll use the property number 1 here. Okay, this is 1, this is 2. So initially I'll use the property number 1. Okay, so I'll just multiply t into sine 2t. So here I have to differentiate it. Okay, minus df by ds, this thing, whole thing, s square plus 4. So what is the differentiation? I'll get s square plus 4 whole square. Okay, in the numerator, if you differentiate, you'll get 0 minus 2 into 2s. Okay, this is again the outside minus. So which will be equal to plus 4s by s square plus 4 s square, right? So this is t into sine 2t. So remember, we have to get this, right? We have to find the Laplace transform of inverse Laplace transform of this. Okay, and numerator, you see it has 2 into 1. Okay, so we have to remove this s term. That's why I'm using the property number 2. So let me use the property number 2. Okay, so I'll just divide by s here, 4 by s square plus 4 square, and what I will do, I have to integrate here. Okay, 0 to t. This is not okay. T sine t. Okay, this is not tau. Okay, t sine 2t. Okay, let me write tau here in terms of tau sine 2 tau d tau. Okay, if I integrate this, I'll get the answer. Okay, by parts I'm doing it. Okay, quickly I will do. Okay, so this is t tau. So integration of sine 2 tau is minus cos 2 tau by 2. Okay, you put the limit 0 to t. Okay, minus integration of, so integration differentiation of tau will be 1. Okay, then we have to do sine 2 tau t tau, 0 to t. Okay, this is I'm doing by parts. Okay, so if I solve this, is minus tau by, this is t by 2, this will be cos 2t. Okay, minus integration of sine 2t, sorry, this is cos 2t, 2 tau. Okay, now integration of cos 2 tau will be sine 2 tau by 2. Okay, if you put 0 to t, you'll get here t here, and here it was originally 2, so it was 4 here. Okay, just apply the by parts integration. I hope you'll get this answer. Okay, so if you do this, you'll get here plus because of this. Okay, and what you have to find? 2, right? So 2 s square plus 4. So I'll bring 2 here, so it will be multiplied here in the denominator, it will become 8. Okay, so this is the answer. Okay, so this, if you find the inverse Laplace transform, this will be the inverse Laplace transform. Okay, so what we got, y of t is equal to, let me write sine 2t by 8, okay, minus t by 4 cos 2t. Okay, let's forget about the coefficients. What you have to focus is this term. Okay, so you see, if your input is, so what is the input that we have given sine 2t. Okay, for sine 2t you're getting this output, right? And you know at t equal to infinity what you'll get, yt will be infinity. Okay, so that's why you'll get unbounded output. Okay, for ut equal to sine 2t. Okay, in the lecture also professor have solved one problem, okay, where he discusses this situation, same situation here. Okay, that's what I'm discussing. I just solved y of t and I'm showing you because of this t term. Okay, so y of t will become infinite, right? So that's why it is unbounded output for sine 2t. Okay, so that's why, so this is one of the answer, right? You have to find out the input for which the system output will be unbounded. Okay, so let's also see for cos and sine. I'll not solve it, but you'll get the point, right? So I'll also see for other two options also. Okay, so I'm just checking for the third option. So third option ut is equal to, what is ut is cos of root 2t, cos of root 2t. Okay, so if you find y of s, it will be equal to s by s square plus 2. Okay, so let's find out y of s, which is equal to p of s into u of s. Okay, p of s was s square plus 4, I think. Let me check. Okay, yes, s square plus 4. Okay, here. So this is p of s, s square by plus by sorry 1 by s square plus 4. Okay, u of s is s into square plus 2. Okay, so you're getting this y of s as this. Okay, so if you just see this, okay, what are the poles for this? Okay, it gets plus minus 2j and plus minus root 2j, right? So this is what non-repeating roots, right? Okay, non-repeating poles. Okay, so that's why, okay, because of this non-repeating poles for a given input, so input was cos of root 2t, you will have bounded input. Okay, so for this also you'll have bounded output, sorry, for given input you will have bounded output because of this. Okay, and if you see this directly, how you could have checked, okay, you see this, I could have directly written repeating roots or repeating poles. Okay, a square plus 4 whole square, and if you see this, so s is equal to plus minus 2j and plus minus 2j. Okay, so these are repeating roots, right? So in this here you are getting non-repeating roots, so that's why the output is bounded. And if you see for the other input also, sine t, okay, same. So let me do for sine t also. Fourth ut is sine t, and let's find y of s, which is equal to 1 by s square plus 1. Okay, let's find y of s, which is p of s into y of s. Okay, so p of s is s square plus 4 and u of s is 1 by s square plus 1. Again you see the roots are what, plus minus 2j and plus minus j. Okay, so this is also non-repeating. Okay, because of this the output will be bounded, right? Therefore the output will be bounded. Okay, so whatever that I am doing here, that's already been taught. Okay, in case you have any doubt, go to the lectures. Okay, so we have solved this question. So only for sine 2t, we are getting the unbounded only for this particular input. Okay, because system poles are here. Okay, because of only one input, you'll get unbounded output. Okay, sine 2t. Okay, so this is marginally stable system. That's why. Okay, any doubt in this particular question? Okay, we have found out the yt also, and in that you can see there is a t term. Okay, so that also uh, give us the answer why it is unbounded here. Okay, if you see this, let me just put this in bracket. Okay, if you want to find the output also y of t, so because of this t term, you'll have unbounded output. Okay, okay, let's solve the other questions because they 12 is also similar to 11. Okay, let's find out. So consider a system whose governing equation is this. The input for which the system output would be unbounded. Okay, so let's first find out the plant transfer function. So this is the governing equation. Okay, so take the Laplace transform. You'll get this plus 3s y of s equal to u of s. Okay, so s square plus 3s. Okay, oh, so what I can do, I can just take s common and s plus 3. Okay, so s equal to 0 and s equal to minus 3. These are the uh, poles of this particular transfer function. 0 and minus 3. Okay, so let's check for inputs, right? So what you'll get. So let's check for first one. Okay, so what will be y of s will be equal to 1 by s. Okay, so y of s will be equal to p of s into u of s. Okay, so okay, let me do one more step and write here. I'll say p of s is equal to 1 by s into s plus 3. Okay, so s into s plus 3 into 1 by s. Okay, so what you're getting finally, y of s is equal to 1 by s square. Again, be careful with this term. Okay, you see, so I'll just highlight this s square. Okay, so at 0, at origin, you are having two poles. Okay, like this, two poles at origin. Okay, this is also repeating poles. Okay, so what can we directly say about this? Okay, so for ut equal to 1, we'll have output will be unbounded. Okay, directly we can tell all what you can do is you can find y of t also. Okay, you can how you can find a by s plus b by s square. Okay, plus c by s plus 3. So I'm not finding out the coefficient, but directly I'll write what you'll get. Okay, you'll get a plus you'll get something t. Okay, 1 by s square. If you find the inverse Laplace, you'll get the bt. Some bt term will come and c e raised to power minus 3t. So this you'll get. So this is s. Okay, so this you'll get because of this second term, bt term. Okay, your y of t will be unbounded. Okay, so this is additional check. So what I had done, I just seen key in the denominator there is a term s square. Okay, so this is repeating. Okay, repeating poles. So be careful with the repeating poles. Directly you can say the system output will be unbounded. Okay, for this given input. Directly you can say, and you can also check by finding out y of t. Okay, there will be t term. Okay, so let's check for the other input also. So you'll see uh, what you'll get. Y of t is equal to, so we have checked for 1, so we are getting the output unbounded. Okay, let's check for cos 3t. Cos 3t, y of s is equal to s square plus 9. Okay, so y of s is equal to p of s into u of s. Okay, so p of s is s into s plus 3, and if you multiply you'll get s plus 9. Okay, so again, what are the poles? If you see 0, okay, so roots will be 0, minus 3, and plus minus 3j. Okay, you see non-repeating again. Yeah, so we have non-repeating roots here. Okay, so what can we say? For this cos 3t, we'll get output. Therefore, the output will be bounded, right? Because you're getting non-repeating roots. You can find y of t also, then there also you can check. Okay, you'll get the same answer. Okay, 3. Let's check for the third. Sine root of 3t. Let's check for this. Sine root of 3 root 3t. Okay, so if you find y of s, what you'll get is root 3 s square plus 3. Okay, because root 3 square is 3, right? So let's again do the same process. P of s into u of s. Okay, so P of s is s into s plus 3. Okay, again into root 3 into s square plus 3. Okay, so if you see here denominator, what are the roots here? 0, minus 3, plus minus 3j. Again, you're getting non-repeating roots. Okay, same. So therefore, the output will be unbounded. Sorry, bounded. Okay, so only for 1 it is unbounded because of this, I think, a square. Okay, last is cos t. Quickly I will do for cos t. Okay, ut is cos t. So what you'll get, u of s is equal to s by s square plus 1. Okay, so y of s is, directly I will write 1 by s into s plus 3 into s plus 1, right? So what are the roots you're getting? 0, minus 3, plus minus j. Again you're getting non-repeating roots. Okay, so again the output is bounded, okay, for the given input. Okay, just by seeing this, whether the roots are repeating or not, we are able to come to conclusion that the system is, or the system output is bounded or not. Okay, only in this particular question, only for 1 we have seen in the denominator we are getting a square. Okay, so this, because of this a square, we came to the conclusion that the output is unbounded. Okay, and we have also checked by finding out y of t. Okay, okay, so only the first option is correct. Any doubt in this question? Any doubt? Otherwise I'll go to the next question, 13th question. We have two more questions, so 13 and 14. Okay, same thing we have to find out here directly. So this is very simple. Okay, so let me write 1 2 3 4 plus 4y 1 2 plus 4y equal to u. Okay, let me first take the Laplace transform. It will be y is for 4 y of s plus 4 s square y of s plus 4 equal to u of s. Okay, this is not 4, we will write ut, u of s. Okay, so this is for 4 plus 4 s square plus 4 u of s. Okay, can you factorize the denominator? What will be the factor here? You see, us, can you factorize this denominator part? Okay, so I'll write this will be s square plus 2 square whole square. You see, okay, I hope this is correct. Okay, we're getting this y of s is equal to, you see here, what you're getting, roots. Okay, plot this. Okay, this is imaginary, this is real. And if you want to plot this will be like this, 2j, 2j, and once again we are getting multiple roots here. So repeating roots you are getting. Okay, 2j, 2j, writing here. This is minus, obviously, this is 2j. Okay, so this is repeating poles. Okay, see, already the system is unstable. So just go back to the class. Okay, I'll just show you where it is. So seeing in the class also for, I think, examples. Okay, so here you're seeing this particular example you see. Okay, whole similarly we are getting so in our particular question we have 1 by s square plus 2 whole square, right? So poles will be 2j 2j minus 2j 2j. So you see, you can directly by looking at the poles we can say the system or the plant is unstable. Okay, so let me find out where that is written here. So here if you see this 0.3, okay, so you have to use this. You see, if there are repeating poles of the plant transfer function on the imaginary axis with all remaining poles in the RHP, so in our case it will be 0, then the system is not BIBO stable. Okay, so system is not BIBO stable. So when we say the system is not BIBO stable, that means for any input you'll get unbounded output. Okay, that's what it says. All right, for any bounded input, the output is unbounded. Okay, because of this repeating poles. Okay, so you see the option, if you see the option C is correct. Okay, so let's first find out if you choose any other option you will find out. Okay, so let me see for this second whether the output is unbounded or not. So we know by definition the system is unstable, the output should be unbounded for any input. So let's first confirm for this ut equal to cos 2t. I'm just checking for one of the input. So ut is cos of 2t. Let us check. I know, but let's check. So y of s is equal to, okay, s square plus, okay, this is 4, right? So let me check y of s equal to p of s into u of s. Okay, p of s is equal to 1 by s square plus 2 whole square. Okay, so I'm just writing here p of s is equal to 1 by s square plus 2 whole square. Okay, into u of s is this. Okay, whatever you multiply, this is the input, right? Okay, so what you will find, Again, same thing. 2j, 2j. So I think 2j, root 2j. Okay, this is root 2. Oh, yeah, s squared plus 2. So it will be root 2j. We're getting these roots. And plus minus 2j. Okay, so you see here, these are repeating. Because of that, okay, you find y of t will be unbounded. You can check for any input, bounded input, okay, for cos of 2t. For any input you check, okay? Just we have check for the one of the inputs. Okay, any question, any doubt in this question, particular question? Okay, because of this repeating poles, the system is BIBO unstable. Okay, that's why if you put any bounded input, you'll get always get the unbounded output. Okay, so the correct option is any for any unbounded input, you'll get unbounded output. Okay, so let's quickly go to the last question. I think this is the last question. Yeah, 14th. Okay, consider the system whose governing equation is given. The system output will be unbounded for. Okay, I think one more question is there. So this is very simple question. I will not check. Let me just give you. You can write down this question and do it yourself. Okay, I'll give you the answer. So consider the system whose governing equation is this. Which one of the following statement is true? So basically what you have to do, find the Laplace transform. Okay, find Laplace transform. Okay, and you'll get the transfer function, right? Y of s by u of s, which will be p of s, and find the poles. Okay, so you just check the multiplicity of the poles, right? You have to find only one thing. Okay, whether you have repeating poles or not. Okay, this is the question. You don't have to find any what is the output for any input. Okay, I think this is very simple. This is very, you have to just find the transfer function and you have to find the factors of the denominator to get the poles and to get the multiplicity of the poles. Okay, so any doubt in this question? Okay, basic Laplace transform and you have to find the roots. Okay, I'll give you the answer. I think the answer is this fourth one. Okay, multiplicity of the. Okay, let's see whether if time permits I will solve the question. Okay, let me see the 14. Consider the system whose governing equation is this. The system output would be unbounded for. Again, same question. Let me first find the Laplace transform. Okay, similar questions. First, you'll see what is the plant transfer function. Its poles. Okay, s square y of s plus 2s y of s minus 3y of s equal to u of s. Okay, y of s. Let's find. I've taken y of s common. Plus 2s minus 3. Again, interesting thing you'll get, okay? So solving is easy. Just you have to get the concept, right? So utilizing these concepts further in the course. Okay. So can you tell me what are the factors here? So you are getting factors as s minus 1 and s plus 3. Sorry, I think somewhere I'm making mistake. Okay. Okay. So this is the, so if you find y of s and u of s, this is the Planck transfer function, right? So you're getting 1 by s minus 1 and s plus 3. So this is very dangerous thing. So I'm getting one pole in the right hand side. Okay. So if you plot in the s plane, what you'll get, this is minus 3 and this is minus 1. Okay. And directly you can tell. Okay. So directly you can say this is system is unstable. BIBO unstable. Okay. Refer to your notes again. This is very straightforward. Once you have any pole in the right hand side, okay, let's say right hand plane here. So this is right hand plane, and if you have any roots lying in the right hand plane of S plane, okay, directly you can say the system is unstable. Sorry, I have written unstable. I will write unstable. Okay. So similar case that we have seen in the previous question. Okay, we are getting repeating poles here. Directly we are getting root on root or pole in the right hand plane. So directly we can say for any bounded input we'll get unbounded output. Okay, so option 3 will be correct. So any doubt, you can put any of the UT given in this question and you can find out. Okay, so you will get, because if you solve this, okay, if you find y of t also, you will get the term e of t. Okay, and at t equal to infinity this term will be infinite. Okay, so that's why you'll have always yt will be unbounded. Unbounded means it will go into infinity, it will have value that will be equivalent to infinity. Okay, infinite. So that's why, but how, before going to y of t, just seeing the poles, we came to the conclusion, okay, that the system is BIBO unstable. Whatever the bounded input you give, the output is always going to be unbounded. Okay, just by seeing the poles. Any doubt in this question? Any doubt? Okay, this question I'll just try to find the Laplace transform for you. Is the last question. Okay, so I think 4 plus 8, 1, 2, 3 plus 22 y plus 24 y plus 9 y equal to u t. For u, I'll write u. So let's take the Laplace transform. It will be, okay, so let me take y of s common, and directly I will write like this. S is for 4 plus 8 is cube plus 22 is square plus 24 s plus 9. Okay, this is the we are getting. Okay, if you want to find the transfer function is equal to this, just ps. Okay, and what you have to find out is roots, right? So how to find roots? For this function, it is q plus 22 is square plus 24 s plus 9. to be equal to 0. Okay, so by seeing the option also, only two roots are there, -1 and -3. Okay, just you have to find the, so just by seeing this order, okay, you'll have four roots, right? You'll have four roots, but we know just by looking at the options, -1 and -3 will be the roots, and just we have to find the multiplicity of that. It's very simple. Okay, so -1 and -3 will be the roots. So it will be lengthy. Okay, let me do. So s -1 will be the roots. So how we can find the, you can factorize this equation, right? So you can use s plus 1 by this square bracket s cube. So this is by hand. I am doing it. What you can do, can -1 and -3 are the roots. So s plus 1 and s plus 3 will be the factors, right? So let me just do s square plus 3s plus s plus 3. Okay, so s square plus 4s plus 3 will be one of the factors, right? You have to find the other factor. Okay, so s square plus 4s plus 3, let's find the factors here. Okay, so this has nothing to do with the control system, but just solving and finding out the roots. Okay, square plus 8s cube plus 22s square plus 24s plus 9. Okay, so this is s square. Okay, plus this is 4s cube and plus 3s square. Okay, this is minus, this is minus, this is 4s cube. This is, I think, plus 19s square plus 24s plus 9. Okay, plus this is 4s. Okay, this is 4s. So let's find out 4 plus 4 is 16s square. Okay, plus 4 into 3 is 4 into 3 is 12s. Okay, so again this is cancelled, right? So I will just do minus 19 minus 16. Okay, so this is 3s square plus this is minus. So if you subtract 12 from 24, you'll get 12s plus 9. Okay, so plus this is plus 3. So this is 3s square plus again 12s plus 9. Okay, this gets cancelled. Okay, this is again minus minus minus, and you will get that thing. Okay, so this is the factor you're getting, right? So the factor you're getting. So one factor was this. So one factor was this, other factor is this. Okay, so we're getting the same factors, right? So this is also like you can write s plus 1 and s plus 3. Okay, same. So you can write s4 plus 8s cube plus 22s square plus 24s plus 9 as s plus. So I'm just doing going to the long way, plus 3. You got this, right? And this is what s plus 1, s plus 3, simple s plus 1 and s plus 3. Okay, which is s plus 1 whole square, s plus 3 whole square. Okay, so what was the question? Which one of the following statement is true? We have to find the multiplicity of -1 and -3. Okay, you see the multiplicity here. Okay, 2, right? So both have multiplicity of 2. So option 4 is correct, right? So any doubt in this question? Very simple. Okay, just you have to find the factors for the denominator. Very easy. And already from the uh, question or from the question it's given that -1 and -3 are the roots. So we know the roots and we just found out the other roots also, which are same. Okay. So any doubt for today's session? Okay. So I have discussed questions based on what was discussed in week 2, right? So I have not discussed anything extra. So these are the questions. These are the assignment questions for the previous semester or previous batch of this control system. Okay. Okay. So you can ask any doubt you have. Okay, we have finished with all the questions here. Okay. So any doubt? Okay. You guys have no doubt, then we'll end the session. So thank you for attending the session. So I'll meet you in tutorial 3 on next Tuesday. Okay, so we'll do the assignment question. Thank you for attending this tutorial. Thank you. Good night.